Okay. Hello everyone. Sorry for the delay today. So I think we're good to go now. All right. So welcome to day 4 of building a game engine using Golang, right? And SDL for our windowing and essentially operating system interface. It's okay. So last time, let's just go on and see where we left off. It's taking a while. Won't go. It's build and run. Maybe building will be faster. It shouldn't. Come on. All right. So while this is building for the first time today, I hope it doesn't stay as slow. We can kind of review what we had last time. So we managed to actually to run an OpenGL window and get some buffers going. We didn't abstract any of this out yet, but we did see that we can create a buffer on the GPU, get an ID for it, bind it to start using it. Then we have some vertices and we set them to the buffer. We kind of fill the buffer with these vertices, right? And that's the amount of vertices, and that's the actual data. And then we set it to a certain attribute. Okay. So vertex attribute pointer, right? And each element that's being sent to the attribute is three elements. So each three, in this case, floats, is being sent to each vertpos. We are not normalizing anything, and then what's this? The stride is 3x4, and then the offset. I don't think the stride is correct, is it now? Let's look at our shader. So this is a vec3. Oh no, that's actually correct. It's one vertex 4 bytes each. That's correct. And this guy is still building. Wow, that's weird. I hope it works. There's nothing wrong with it. All right. So one thing that's missing before we abstract anything out is actually colors. And it will be interesting to see how we can use the same technique for buffers to do colors. It's because last time, when we did the old way, the fixed function pipeline, without any buffers, we managed to also give colors to each vertex, and then the GPU automatically blended the colors between the vertices, between the different points. So how do we do this in this case? And thankfully, that's actually... Hey, baby John, welcome. Welcome to the stream. I hope you enjoy watching us build the game engine. It's just this. So we wanted some colors, and we can actually use exactly the same stuff. We'll make a new array for the colors, and we'll make it essentially match, and then we'll do the same technique here. So let's just first update our vertex. So for each vertex, now we're sending more data. Originally, we were only sending position. That's kind of the minimum you need. But now you can say, hey, you know what? I actually want to send a color. And, let's say it's RGB only for now. We can do RGBA if we want transparency. But if we want RGB, it's a vec3, and we can say, okay, it's maybe vert color, right? And we'll see how to deal with it later, but for now, at least, we know that there is for each vertex also a color component, and you can actually add as many as you want. Okay. Now, how are we going to do this? It's the same idea. We're going to make a buffer, because a buffer is just kind of an array in the GPU. It doesn't mean anything until you say, hey, send it to this variable. GPU doesn't really care what these values are or what they mean. You decide what they mean. I might as well just send this vertex array as color values. Right. So I'm going to repeat this. We're going to create. So let's assume this part is for the vertex position. Now we have color positions. All right. Now instead of, let's call it a color, right? Color VBO maybe. Color VBO. I'm not sure if it's accurate to call it a VBO in this case. But yeah, it's a color vertex buffer object. We're going to fill it up, so we're creating a new buffer, right, for the color. We're going to bind it, so we're basically telling the GPU again, hey, we're working with this specific one, with this buffer, and so we're working with the color color buffer now. And we need a bunch of colors. So in our case, oh, it built. Here we go. I know. Okay, so we have our quad made up of 2 triangles, which you can see here. 1 triangle, 2 triangles, right? And kind of 0 zeros in the middle, and then maximum is between -1 and 1 on both x and y axes. So this is kind of halfway, 2 triangles. So for each vertex, we're just going to assign, hey, this vertex, this color, that color, so on. So we said, hey, we're working with this buffer right now. Now we need a buffer. We need a bunch of color data. And I think you're forced to actually, and it makes sense, to have it the same size of vertices. So you cannot have like, okay, half of these vertices have colors, half don't. Doesn't make any sense. Potentially it gives it a default value. I'm not sure. But yeah, in general, you need to match these. So now we're doing RGB. And so these must be, I think between 0 and 1 works. So 1 is like full red. 0 is just like no component here. So if I want red, we want a red rectangle in this case. So I'll just make everything red. Right. And that's it. So we're saying for this vertex, this is the color. For this vertex, this is the color, etc. Or at least this is what we will do right now. So we have this color data. We need to put it in this array, which we made here, the color VBO. So we're going to buffer it. Let's see, 4 bytes. Yeah, so that's the size. 4 bytes into the number of colors we have, which is the same as vertices. Then we get a pointer to all our colors. We send that. And static, we're saying, hey, we're not going to change this later on. So all is good. That's it. So color positions, then load colors into color VBO, and then same thing. Now we're going to tell the shader program, like, hey, this is kind of for this shader, load it into this variable. So we call the variable vert color, right? That's our in variable. So it's going to say, give me the position of this thing, vert color position, vert color lock. And then, okay, on this location, we're giving 3 values, right? The size of one, all of them are here, right? We said 4 bytes each, and here we're saying 3 of these 4 byte sizes. So 3, 3, 3, and so on. They are all floats again. Yes. No, they're not normalized. Stride is the same. We just jump. Yeah, it's tightly packed. All we have is colors. So 3 colors into 4 bytes. So we jump 12 bytes each time to go to the next color. And no offset. That should be it, honestly. here, and then we just enable it because for some reason you can disable these things. Yeah, I guess it might be useful in more complex cases. So now if we run this, nothing should happen, but at least it should compile without complaining. So if I just to get to a command everybody uses, go run, there we go, nothing. So no compilation errors, nothing is wrong. Now we didn't use it, that's why nothing's happening. So we are passing something, we're not doing anything with it. What we need to do is we actually need to send this color from here to the fragment shader, because our colors for the pixels are actually in the fragment shader, not in the vertex shader. Vertex just per vertex. So if we have like 6 vertices, it's running 6 times, but we have thousands of pixels in that rectangle. And the way we do that is we say an out. So we're outputting some data from the fragment shader to the next step, which is, from the vertex shader to the next step, which is the fragment shader. So I can say, hey, I have an out, it's a vec3, and it's out color, right? Let's say vert shader out color, right? It's too long, so out color. Now we need to match this name. So we have this variable and we're going to fill it up. So out color is just vert color. We're not going to change anything. We're just saying we're copying it there. And then this thing, since it's an output, the final, like the position output is this GL position. So this output is just a variable that is passed to the next stages, in our case, the fragment shader. So we're going to take the same thing as an in. So here, in, and these need to match. So this thing, the name of this and the name of this needs to match. So the output of this variable, or whatever that variable is going to be sent here. And then instead of hard coding white, right, we can just say, hey, without whatever we receive from the fragment shader, put it and let's go. So go run again. And you should see, right, there we go. Nice. Now, the interesting part is if we don't make everything red. So let's say this thing is top left. So let's take the bottom half, or the second triangle. So these 3 are red. Let's make all of these blue instead. So kind of the triangle making half of the rectangle is red, the vertices are red, and then half are blue. So we're only defining absolute red and absolute blue. But if we look at this, there we go, exactly half. Now, in between, the kind of the GPU is filling in the data. So we only have 6 vertices. So what's the color of this specific point? So the GPU is saying, okay, what are the closest points? So in this kind of, for this pixel, the 3 closest vertices are all red, so the color is also red. If we change that now, if we make only the top, let's say only the top left vertex is red and everything else is blue, we should see interpolation. We should see the color gradually changing. There we go. So all the 4 or the 3 here vertices, top right, bottom, and bottom left, they're all blue, and only the top left is red. We never really interpolated. We never made this gradient, but the GPU, as it's sending this output, it doesn't actually send it exactly as is. It kind of interpolates, it estimates the color in between these points, sorry, and we end up with very nice gradient like this. Right, so now we can, and we can do more, right? But I think for now this is pretty good. We are doing, let's see, vertex buffer objects. colors. We can do maybe UVs later on if we want to do texturing, probably. I think this would be useful, and so on. So we have we need the ability to be able to say, for this vertex, add all of these buffers, all of these attributes. We don't want to be limited. We don't want to write all this code every single time. We kind of just want to say, hey, take this and put it there. So I think the best thing is to abstract all of this into some classes that handle all of this for us. So let's see. I'm not exactly sure, of the best way, but you can start that this is working. Oh, actually, before that, we have VAOs as well. Yeah, because I want to get rid of compatibility mode. So the last thing is, yeah, that's right. The way we're drawing now is, it's 6, yeah, simple shader. Okay. So this vertex buffer object, right, for this set of vertices and these colors are connected. Right? This is very important kind of concept in this case. I might have two different rectangles on the screen. One is, and they might be in different. They might be using different set of vertices. So I loaded two characters, two models, two different 3D models, for example. So each is going to have its own list of vertices. It's going to have its own colors, etc. But for each model, the list of vertices, the list of colors, UVs, anything else we have on vertex, any vertex information, is connected. I always, when I say show this list of vertices, I always want to show this list of colors along with it, right? I want to associate kind of these two all the time. So we want a way to connect them in kind of one big object where we simply say, draw this object, and the GPU knows, okay, I want this list of vertices, this colors, etc. And this thing is called VAOs. Think vertex array objects, right? So vertex array objects. Essentially, an object, like a struct, containing multiple VBOs. Right? In this case, you have two, might have more, and we can just say, draw this VAO, draw that VAO. So as soon as I flip the VAO, I'm going to get a completely different thing drawing on the screen. So the way is very similar. Instead of creating a buffer, just before it, we're going to create vertex array. Yep. We want one, same thing. So VAO ID u20 VAO ID. We're going to create it and bind it. And I think that's it. Bind vertex array. So we're just saying start using this. And then at the very end, when we're done, we can just say, okay, stop using it. So if you bind to like 0 is an invalid index, it's not really a pointer. It's just 0, doesn't point to anything. So here we, like for example, we bound the color VBO. Okay, so we're using any changes we make, any bufferings, all applying to this color VBO. Now, if we're done and we don't want to make any mistake in affecting it later on, usually at the very end, we're going to GL bind buffer again, but GL buffer arrays. Sorry, array buffers. Right, bind it to 0. So we're saying clear the binding essentially. So even if I write some code or I make some wrong calls, it's not going to screw up my color objects. The same thing for the vertex array. So the nice thing is there shouldn't be anything else that we need here. OpenGL, since it's like a state machine, it remembers. So when we bind this buffer and we fill it up, it's remembering that, hey, you also have previously bound a vertex array a vertex array object. And so I'm going to record that this VBO, this vertex position, is part of this object. And then similarly, since that VAO, remember, as long as the types are different, like we're not binding this, binding an array buffer is going to override all array buffer, and a VAO is a different kind of thing. So this is still bound. We do this, and that is added to the VAO, and then we do the color positions. So color positions, color data, right? And that is also going to be recorded in the VAO. So it's like having a struct with two arrays right now on the GPU. And now that we have this, and then we are done working with them both, we can clear them. On the main function, or when we're drawing, we can, I think, draw. Oh, draw array is already new. From array data, this should have been draw. I think draw buffers the old way. Yeah, draw VAOs. Let's consult our friend turn OpenGL, and let's talk about shaders. So we are about we're done with all of this. Vertex array. Okay. Oh, okay. Yeah. So, draw arrays. So draw arrays is going to use this VAO, right? All of it. Okay, perfect. We're already doing this correctly. Draw arrays. This should have been draw buffers. That's the old way. Drawing buffers only works in compatibility mode. If you try to do it in the new core mode, in the new OpenGL, it won't work. It won't show anything. So in our case, I don't think this will show anything because we unbinded the buffer. We can try and see. Yeah, nothing, right? This is, and very important to understand, is like the kind of the state machine behavior of OpenGL. Since we removed any binding from the vertex array, when we tell it, hey, draw the array, it's like, what array? I say, which array should I draw? I don't know, I could have multiple. And maybe we can output this. So VAO ID and we can use this instead, right? Just to illustrate. VAO, that's it. We create it, and so now we just have an ID that's accessible from our side. So now, since at the end of this function there is nothing bound, if we run it again, it's just a black screen. But if we bind array, right? Bind the vertex array using that. So it's buffers.VAO ID. So you say, okay, start using this, and then draw. It's going to remember both buffers, the vertex buffer and the color buffer. It remembered the colors and the vertices both. So it's kind of associated them in one, like in one object together. So we don't need to handle, if we're abstracting this, we only need to remember probably the VAO. We don't need to keep track of all the individual buffers unless we want to change them, I guess. All right, so this is good. Now let's start working on some things to make our life easier. All right, now let's see. So how are we going to do this? By VAO, potentially we can just do create new buffer. We have a buffer. Let's try some more friendly names so you don't have. Yeah, if someone is using this, we don't want them to know the details of OpenGL. So some kind of easier names. Anyone have ideas? Okay. vertex array, new buffer. I can just honestly plug it all in a buffer. So if we have a function like new buffer, give us back a buffer. And a buffer is going to have a VAO ID. Which is int2. We're going to have a number of, we're going to have some number of vertex attributes, like color, blah, 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 whatever, anything per vertex you need. So potentially, we can have an array, honestly, of all the different buffers we have. Okay, let's call this a buffer object. And maybe it's just a single buffer. Single buffer is ID. So maybe you have a buffer type, which can be an array buffer, for example. Yeah. Buffer container buffers container. All the names are random. Let's just go with object. It's going to contain maybe an array of buffers, some amount buffers, I guess. And this array is some kind of type. Let's call it buffer type, just a string. Actually, it's in it. Then we can have a bunch. Let's see, const. So like array buffer type array buffer. Let's do this. The buffer type that is equal buffer array buffer. Keep mixing them up. Okay. So we can have a bunch of types. Maybe I'm overcomplicating it, but let's go and then see how nice it is later on. Buffer type. We need the buff. It's the type an ID, which is an int. And here we have a bunch of them. Bunch of buffers, VAOs. Okay, a new buffer potentially, I think, just allocates one. That's good enough. And so we can do buff. Actually, it returns buffer objects. Project. Right. Now we can create one vertex array, and then we can just return buff object. Need ID there. The ID is this ID. Okay, and now we have our buffer. Now we just need a way of adding a bunch of buffers, right? So potentially we just do on the buffer itself, we can say VAO, right, for objects, add buffer. We go gen create. It's like adding to create buffer. Yeah, let's do. I think you can change the name. So all that's going to do is essentially implement this functionality for us. So we have our VAO. You can just bind it. Then we're going to create a new buffer like this. We're going to create it, create one buffer, VBO. We're going to bind it, and then we're going to work with some kind of data. Now generics would be nice. We'll go generics. That's hopefully coming soon. But gen buffer, yeah, maybe. Oops. We'll need probably different ones. So someone will need to send us a slice, and yeah, some kind of, maybe we can take an interface, honestly, but then we won't be able to simplify this process. Yeah, so I guess we'll just float 32 till float. So data is an array of float 32s, right? Someone's going to send us kind of, hey, take this buffer and create it. So we don't need these anymore. We're going to just take the data and a pointer to it. We're done. VBO ID, and we're doing all of this with respect to the buffer object we created before. And let's see. What we're going to need is the type, right? Which is actually we don't need the type here. Maybe do array buffer. Array. Okay, so we're going to assume it's an array buffer. For now, yes. So if we have now a buffer object, b buffer object, ID is this VBO ID that we generated, and then the type for now is an array buffer type. And then we can just pass these. So we create it, we create the buffer objects. We do this. Maybe we can stop using these. There you go. Just go enter 2. 4, because we know it's a float that's coming in, right? So we can just say, hey, 4 bytes. And this potentially, yeah, this probably we want to kind of control. So we have, I think, 3 things: static, dynamic, maybe this one. Yeah, stream, static. Okay, so we can make another type. which is type buffer usage, again an int. Let's confirm, is this an int? Yes, yes. And let's just say buff usage is gl static draw, and this is buff usage. So once and use many times. Static, I think static is clear enough. We can at least put our own comments on this so no one gets confused. Stream. And these are actually very good. And again, thank you very much. Buffer is set only once and used the GPU. Dynamic. Stream. All right. Buffer is set only once and used many times. So I think the most common case, actually here, is this. Is the static. And then dynamics when things are moving a lot, animated or something. Okay. Buffer is changed a lot and used many times. It's good. Okay. So we just say data and buff usage is buffer usage. There we go. Now we can replace this with our own nice commented stuff. There we go. So we don't have any more. Well, at the end, that's the nice thing. We can also make sure that we bind vertex array, we unbind. So if someone else comes along, it's good. So generate a new buffer of floats. Let's say create vertex buffer object. Bind it, use it. Oh, we also should unbind the buffer itself. And I think we should unbind. Yeah, I think we should unbind after the bind buffer. Okay. So we create it and build buffer data, right? And then buffer. Okay. Think to make sure we can check bind 0. Yeah, I don't really unbind. That's fine. Okay. So now we have a nice little object function that does all the work for us. It's fully abstracted now. I think we have our own types that are explained. So this is generic array data. You define what it means. We just need now to add it to the list of buffers that we have. Okay. So at the end, we can just say VAO.buffers event. Actually, do you have to make it this one? See, Yeah. Why buffer? This is an array buffer. I wonder, you can check like here. What is the array something buffer? There's an array buffer, and oh yeah, there are depth buffers and so on. Why makes sense to have a choice, or we can make multiple functions later on. Depends. Generally of gen I guess type, and then instead of, so this is not hard coded anymore. And yeah, you just do type. All right. So we just need to make sure if someone were to use this, they're not proficient, I guess at least this should be simple to read. Should be used for most data like positions, Vertex colors. Right, so now if someone hovers, they get nice. Okay, that's it. So we add it. Now, if we have a buffer, we can say use to bind. Right. Start using, stop using. So project start using, or maybe activate. Deactivate is nice. Just activate basically just binds the array, right? And then for on deactivate, well, is that's too much. There we go. Nice. So this and this are both now done. We should error check more, honestly. We get 0. Yeah, I can do that later. Let's test this. So no more this. Right. Let's just copy these two to main. Load shaders, buffers, add the buffers. Maybe let's make it's just for now. We don't need this anymore. Load shaders, let's just make buffers. So now usage from the outside becomes relatively simple. You have some data, probably you load it from some file, right, which gives you vertices, colors, whatever else, and we can just put them. So we can do buffers dots. I don't think we need any of this anymore. We know soon enough. So we have this buffers, new buffer object. Nice. Okay. Buffer object. So you can say gen buffer floats. One time we can pass our vertices, and then the buffer type is array buffer. We don't really have anything else now. And usage is static, right? And one can always look and see the comment. Create the buffer. We get another one, same data or different data, but the same settings on it, and that's it. Very nice. We can put this on the top so we have access to it. So we created. We should actually create it after. Yes. Yeah, let's find it here. Let's use it. Yeah. Okay. So we create and then just load using 2 lines. Very nice. And here, instead of using GL stuff, we can just do my buffer object dot activate. We're done. Dot deactivate, and we can make sure no one is, overwriting anyone else's work. Let's throw this, and I think we're getting close to actually being able to make a small game. Okay, it's black. Black screen. It's UI. So something is not binded correctly initially. Maybe we need to unbind this before. Can check. Yeah. Let's see. So Gen VAO is just C switching. Not sure. Okay, not that. All right. So you have the buffers, buffer type. You have the VAO got created correctly. You have each VBO is a new buffer with its type, which got set correctly as well. Buff type is just do this as well. A VAO just failed to create OpenGL. Shouldn't be failing, correct? Okay. So these look good to me. Then we bind the Vertex array ID, and then at the end of the draw call, we unbind. This looks correct, honestly. You have the colors. Okay, I see. Is there any difference? Blend colors, pointer to a color, to the colors. Okay. Oh yeah, of course. So we're loading the buffers and we completely forget to do the attribute stuff. All right, so we have the data in memory, but we're not passing anything to the shaders. Okay, so this is another thing the buffers have to be able to do. I'm not sure if this is actually part of buffers or not. For now, maybe we can put it there. Or actually this is part of shaders, maybe. Yeah, yep. This is working with the SP. Yep, it's part of shaders probably. Yeah, I think it makes more sense there. So we have the buffers. Now we tell the shader, hey, take this buffer and actually use it. VBO. This thing. Yeah. Yep. All right. All right, cool. So we have our shader program, which we can use to get attribute locations already, which is good. We have some shaders in the program, and the program itself all right, so we attach, linking, get attributes. Now we also want to load attributes and enable disable attributes. That's another thing. Might make sense to cache these, but we can do that later on. Okay. Yeah. It might make sense to cache instead of doing the string stuff every single time. To cache the location of the attributes. Anyway, we can optimize later on. So use maybe we can call it enable disable. Enable activate. Let's be consistent. Activate and deactivate. And in that case, we just don't use anything. So get attribute, then we can do set attribute. Let's move all of the attribute stuff down because I think it will get kind of long. Okay, program set attributes. Yeah, because here the naming is horrible. Vertex attribute pointer, just to kind of set it. And I think it works by being bound by this, by binding an array buffer, then it knows which array buffer we're talking about. Otherwise, it doesn't make sense. Vertex attribute pointer, right? Because we're not passing any data, we're simply saying how to use it. So yeah, it's by binding. So nice thing is here, our shader can reference that. So set attribute is all of this. Right, as a comment. Okay, set attributes, attribute name, thing. Attribute location. Yeah. So in this case, we're doing this. Name. Attribute. Okay. And now we have this location. We do need set this attribute what? So we need a buffer, not a buffer object. We need a specific buffer to know, okay, we're dealing with this. Buff is buffers dot so you need one single buffer, one specific buffer that we're talking about, and then this bind and bind. We get the location, we bind the buffer. Oh, it would make sense to also have a bind on the buffer itself. We have a bind only for the buffer objects, for the entire buffer object, but it also makes sense to have it for the buffer. So let's make that func the buffer. And then we can also say activate. I mean, this is kind of lower level. So use that. Activate, deactivate. Yeah, let's go with the convention. Activate. And here it's just gl bind buffer, and it's you have a type, you have an ID, good to go. Deactivate, very simple. I think we're starting to get a nice interface for stuff. Getting easier to use. Okay, so we activate, we set the data. This is potentially, we can abstract it out if people want to disable attributes, which I think makes sense later on. And then we can, instead of this and this, buff, deactivate. So set as get attribute location, set attribute, and shader program, enable attribute. Yeah, this is shorten attribute name. Here also set attribute. Yeah. So at the end makes sense. Send enable attributes. Get name. Activates. Do the thing. Okay. This is actually something we do need to know, which is this. Yeah. If we assume, which might be dangerous, but I guess for a very long time it's going to be okay. If we assume the stride, like the array is always tightly packed, we only have one type of object in the array, so we don't have an offset, we don't have a weird stride. And then it just depends on this, like the buffer needs to contain maybe more information for us to be able to do this properly. Because the buffer type is what, like array buffer. We need to know the data type, and based on the data type, we can get the stride. So let's see, we can change it later if that does work, doesn't make sense. But in data type, data type is an integer, and data type float 32, and we can just have it equal to the number of bytes directly, so we can calculate these properly. So this is just one float is just 4 bytes. For example, let's just do a few common ones. Int 32 is 4, is 8, and we have the other things like vec, very common ones, right? Like vec3, vec2, vec4. These are the ones separated by open. So vec2 is data type float 32 into 2. Yeah. Here into vec3 is 3. Vec2. Yeah. Vec2 is always float. I think vec2, 3, 4. There are other types of vectors, but they would usually have like a letter at the end or something. By default, vec is just a float. So this gives us the stride. So this thing is for a vec3 only. So in the buffer right now, we can part of the buffer information that we would need is an ID, its type. So the GL, the buffer type, then we need a data type. Which is one of these, right? And in here, since like we know this is a float, we can just do this way. Type is what type? Floated. Sorry. We do need to know. Yeah, someone needs to give us this information. We don't. It's a float. It's one of floats. But we don't know if it's a vec. Is it a vector? If it's a vec, what size, and so on. So we need to know actually. Yeah, if you're sending us a vec2, then yes, it's floats, but it's not 4 into the length. This is actually correct, right? 4 into this text. I think this matters for not for buffering the data. Buffering data just like take this whole thing and put it there, so we don't care about the separation, the usage of the data. So yeah, this is fine because we know a float is this much. we can make it nicer by using this. Right, you can just make this an int. It's just nicer. So the length of the data multiplied by whatever the size of, so just we don't have magical numbers in there. Everything is named. But it matters when we come to put that data to a variable, to an attribute in the shader. We need to specify, okay, sure, you have this many floats, like 10, 20 floats, or 100, whatever. How are they separated? So then, not only is the total length or the stride important, but how many, I think. So vec2 is this many bytes. And let's just look at this. So we need to know how many element, maybe we call it element count. So how many elements, and then what's the stride between these elements? Stride is straightforward. Stride is just the data type itself. Maybe you can make this a struct. So something like data two is just kind of. So we have a stride for the data, which is an int, or just give it some nice name, byte size. Size, yeah, let's go size, just an int. What else? Num of elements, or element. Is the size in bytes of the entire data type. Is the total size in bytes of the data type. E.g. for vec3, vec3 size equals 4 into 3. 4 bytes floats, and that by 3. So this is the size, and element count is how many primitives make up the data type. E.g. 3 for vec3, as it's made of is the 2 for vec2, 1 for float, 2 for vec2. Yeah, makes sense. Element counts, yeah, size, which if you divide you can get this, or we can do it the other way around, where we have element count and size per element, and then we can multiply them to get the stride. I mean, for at least this thing, we don't need this extra calculation. We need the stride all the time. I mean the size, the number of elements. I'm not sure. Element size, element count. Element, yeah, yes, so this element size is the size in bytes of one element the data type. Okay. It's then we can give some we can give a small function to do this. Maybe we can have a data type here as well, so we don't have to hard code. Yeah. Yeah. Just kind of thinking what's the best way to abstract this into a nice, easy to use format. So you can have struct with these. We can have some functions on it that we just call, and we do like buff.getStride, buff.get number of elements, etc. And that makes it super easy to fill this up. Let's just implement this while we're at it. GL enable Vertex attribute array, and it's get attribute location attribute name. Right. Hopefully your attribute name is correct, or this will crash. I really want to get rid of all of these string conversions. Every time we want to do something we look up, we might as well cache, or just like have strings, like add attribute, and then just kind of stores these. I'm not sure. We can care about that later, honestly. Okay, enable attributes, disable disable attribute. Go. Okay. Back to this. So when we're creating the buffer, I mean, these things can fill up. So we have kind of our magic numbers here. We can have a supporting type. So this is data type size. And since we know this is a float, the data type size is data type floater 2. Data size type size. Shift and Alt. There. Type size. Type size for 2 and type size with 2. So this is the type size, and then our data type can be an element. An element size is one element count, and this honestly is just that. So instead of the whole thing, this is just going to be, okay, float, basically the element size, right? Is the data type and data type element size. Then these don't make sense anymore. This is hard. Okay, or annoying, right? Not hard. This change this. So our data, our buffer is now this thing, And we just want an easy way. Let's just put all of this in the function potentially. So we can have, if we really simplify it and maybe let go of some performance, like buff data type. Right. It's the same. Okay. It's elements. Let's do element count. Let's forget this for now. So here we know it's a float. So this is actually 4. Right, and this is buff.data size. So you have the type of the buffer and you have type of the data. And then you have the type of the data. And then we have the data count. Yeah. I think, yeah, let's just combine this with this. So our buffer just contains all of these. So it has ID of the buffer and type of the buffer. And then we have data type. We can just actually put it inside. Like this. Data type, and this is just data type, and it's just going to include these things, the size in ints, in bytes again, and the, let's go do the size element count. So this is size in bytes of one element, e.g. for vec3 it's 4, one element. And this thing, just like we did before, right, is number of elements for vec3 it's 3. So you can just multiply these, right? So we have this data type, it's included in the buffer, and then when we create a buffer, we do this. Data type. And then since this is actually in this case we still don't know data representation. Yeah, we can change it. We can ask for this. So we can have a function, func new data type, or something like gets data type. You pass something like you tell us, hey, it's a float, buffers to type, okay, let's call this data type info, right? And then data type itself is just an int. That's an iota. So we have like data type float, just like we did before, right? Float 32. Doesn't mean anything. I think just we're going to use it for a lookup, like in a switch case. So let's try a few. So yeah. Int 32, float 64. We don't need these, so this is automatically going to be incremented from 0 all the way to 1, 2, etc. We can do unknown. Usually that's a good idea. Unknown. Right. float, and then we're going to do a data type vec2, vec3, vec4, and here we can just switch on those. So we can switch, we can take this as an input data type. You can say, hey, is this, for example, an int32? And we're going to return get data type info, right? We're going to give back data type info struct. And all we're going to do is kind of have one place where we define this kind of information. So we don't have it all over the code, or it's like, oh, it's 4, it's 5. I really don't like, magic numbers usually lead to a lot of errors and confusion when someone comes later on to read stuff. So element size, so for the size of one element is 4 bytes, right? And 1 element. That's it. And we're just going to, where's the problem? Yeah. In here, we'll delay this for a minute. Buffer is going to have a data type info. Data. Yeah. This is what? Buffer the data. Okay, the total size of the data is how long the data is. It's buff data type info. In this case, it's the element size multiplied by n elements. Actually, element size by element count by the, yeah, so we can have a function for this. So yeah, we have this, then we can just do more cases. Why are you okay? Return data type info. So if we didn't match anything, we can just really do a default case here. In the default case, we can return data type info, just like it's going to be 0 everywhere. And we have data type float32. Let's just do all of the cases we have right now. Int 2 floats, vec2, 3, and 4. Now, for float is the same for this one. Element size is 8. Element count still 1. For vec, element size is the same. So it's basically 1 float, but we have 2 of them. And here we have 3 of them, and here we have 4. So we have all our kind of numbers in one place, which is good, very nice. I think now we're starting to get something very nice going on. Data type info, and now okay, so move this kind of up, and we move these into their own files just to get things nicer. Now we can do a function, DTI, right? Data type info, and you can say get total size, get size, right? And that returns an int. So all it does is returns element size multiplied by element count, and that's our stride. That's the stride we need. Yeah, this is probably going to be inlined everywhere, so it's not going to be slower, shouldn't. Get size returns the total size in bytes of the total size e.g. for vec3 is 4 into 3, right? 4 elements or 4 bytes into 3 elements. Okay, here we go. Nice. And now our buffers, let's just move this to its own thing. So data type go. Yeah, I guess we're moving. No snake case. Yeah. Buffers. So now we can take data type and data type info, and this thing and this thing. Move them all into this. Data type, we have data type info and its functions, and then get data type from the data type. Perfect. I think that's it. We're really looking good here. Maybe we can log in this case. Logging dot or log. Different line. Unknown data type and the data type is DT. Okay. So our buffers now, they include all the information needed. There isn't magic numbers or context. If we create a buffer, then we know for a fact what it needs. So we have our buffer usage, right? These subtypes. I don't think we're using this anymore. This could, yeah, this got abstracted into, we don't need this. So you have a buffer object containing a bunch of buffers, and each buffer is buffer ID and type, and then info about the data stored within the buffer. So then when someone generates a buffer, they tell us what the type is, how it's going to be used, and then buff data type. So they need to pass us just the type. What kind of data is this buffer including, right? And then we can use this information wherever we need to later on. So here, that's nice thing. Data type info. We can just do get data type info from our data type. We're good to go. Now, in this kind of thing, so we have all the data multiplied by the size of one piece of data in this case. So we multiply by the element size, right? Because we are working not with the, like if this is a vec3, it's not like, okay, there are 12 into this many vectors. This is, we're working with the individual elements. That's why in this case, we are using the element size. Okay. Now, in the attributes, on the other hand, which is why we did all of this, when someone sends us a buffer, we are not working with the individual elements. We are working with the buffer as a data type, because now we are specifying, like this could be a vec3, right? So in here, right, how many elements is this? So we can just do buff our buffer dot element count. This is how many elements we have, and then maybe we can make it in 32. Sure. No, we don't need that. Okay, and then this is the total size now for one piece of this, for like one variable of this type. How big is it? So in this case, this is the elements into element count into the element size, which you have just kind of say get size. So you can just do buff dot get size. That's it. And no offset, we're assuming tightly packed. Now we do need to know the GL type from this. Should be easy enough. We can just do not on the buffer, but yeah, I mean here we're going to have to say, okay, here's the GL type, so we can just get it back next time because we don't know if this float. Is this buffering for data type? Interconnected. So buffer and yeah, let's just put data type info, makes more sense. So we have element and GL, right? And it's like GL dot float, which is these are all ints. Yeah, they're all ints. So this is just an int GL type, and in here now I can just do GL type GL dot float. I think float is just already. Oh, sorry, this is not float. This is 32. I assume an int is already in 32. I hope so. Int 32. Yeah, I guess it's that. And what? GL. Okay, here. Float is just GL type. Float. This thing is a float 64. It's a double. Double. Right. Vec2. That's GL. Float vec2. Right. That's the default. So when we say vec2 or vec3, this is a float. I think there's like yeah, vec3b. I'm not sure where you put it, but you can do like I and F and so on. You can check that later, honestly. Yeah. So that is vec2. This is vec3. That is vec4. Doing good. Now in our shader, where's the shader? Yeah, the shader program. We have get size, and we have the side. I hope this works well. We might need another function, or we might need multiple functions for set attributes, for like set attribute float or matrix or something, but we kind of encapsulated all of that into the data type itself, so we don't need multiple set attribute functions. Okay, so instead of this, we do buff dot GL type. uint. If you want the uint, then we can give you uint. Okay. There we go. We're done. Very nice. To make this shorter, potentially we just embed the type within the struct. And if you don't know what this means, like it's kind of like inheritance, not really. So when you do this, you still have the variable inside, and you can do all kinds of things like this. Very normal. Or when you create it, you can set it, etc. It's normal. You can use it normally. But the nice thing is it gives you kind of a shortcut. It gives you a shortcut where you see the things inside of it at the top level. So you can either write buff.dataTypeInfo.elementCount, or you can just do buff.elementCount. Exactly the same thing, because we embedded the type, almost like inheritance. So now we can just shorten all of these, and even the functions apply, right? And we're good. So we just send, here's the buffer, here's the attributes. We shouldn't enable because we have that separately. We have the attribute location, activate, set the data, and set attribute location. I think that was nice, honestly. Get attribute location. Let's do uint as well. For some reason it returns an int. I'm not sure. Yeah, just do shorten. Looks nicer. Okay, and we're done. So this shouldn't care now. Should have all the information needed in here, and enabling is just this, disabling is just this, and we're good to go. Fragment ID. Any questions? Okay. So now this should actually work. Gen buffers need a bit more info, but it should be the good thing is, yes, it is still a bit long, but at least it's a lot easier to understand. So here it's buffers dots. So this is what we know. Our vertices are vec3s. You can just do vec3. Our color data is also the same. So you can do that as well. Now that should do it. This one. Oh, still dark. We need to enable. So we actually need to enable the attributes. So now load shaders, load buffers. So once we have done that, you can do view. Well, we need to set and then load as well. Load the buffers as well. So we load the shaders, we load the buffers. Let's take this. For now, we're just putting it at the top. This thing. Buffer objects. So let's just do it in this. Okay, we did this. And then, so we load the shader. We have the shader now. We have the buffers. Now we can combine. So we can do, what did we call it? Shader? Simple shader. Simple shader dots set attribute. Right. So first, let's set the vertex position, just like our name here, and which buffer. And then we can say, well, in this case, we have the buffer objects, not buffers. We know we can make a nicer way of doing it than getting it out of an array, but we know for a fact that we loaded the vertices first, and then we did the colors. So we can do this, colors, and then we can just enable both. Enable attribute here, and that should do it. Let's see. We're still getting black screen. Did we forget anything? Enable, I think we need to activate the What did we have? What did we forget? Enable attributes. We need to activate the program, which I think we're doing. And doing the thing. Does deactivate, activate, deactivate, activate, deactivate. Okay. Where is this? Set attributes. Okay, vert pose. Oh, it's vert color. This is the problem with strings. This is why should get rid of it as soon as possible. We need a nice way of doing that. Okay. So that's one thing. Enable attributes. Just shrink all of this. Load buffers. Generate. And we set them. Array buffers static. Vec3s, both of them, yeah. Just make sure we are gem buffer floats. Do we need float anymore? That's one thing, because we have everything in the data type. We don't actually need this. Potentially we can send an interface, just an array of some data that we don't care about. We don't care what exactly it is. Yeah, we can actually just send interface. Interesting. Ooh, actually, this takes a slice or pointer. No, yeah, that should work. This is a slice or a pointer. Okay, yeah, this is fine. You could be doing some wrong math somewhere. Enable it, and then I wonder if we have to bind the entire VAO. I'm not sure. We can test, definitely. We can maybe. Oh, we were binding this array first. Okay. Let's see. There, activate, draw, deactivate, swap. Nope. Still not working. Okay. I wonder what I missed. We can start debugging soon, and we need to make sure that the arrays are actually correct. Vert pose, vert color, simple shader. All right. For now, I think this is not. Doesn't matter if it's a float or not. Since we have data types now, it's completely generic as far as the function goes. Create the VAO and we bind VAO. Now I hope we don't have to pass all of them. I don't think so. We can bind in multiple steps. I'm not sure. Let's consult this. Bind it. The corresponding and attribute pointers, and then yeah, we might need to bind the VAO, not just the buffer. Let's try. So when we set, we don't just bind a buffer, we might need to bind the entire buffer object, maybe. For now, let's just do something stupid and kind of let's take this code just for testing and put it right here in main. So we have our simple shader, and instead of this, let's plug in this thing. So we have buffer.activates. Okay, let's just go there. Objects. Here, this is the simple shader, and let's say we're dealing just with let's do word position first. Okay. VAO.buffers 0 0. Yeah, size, and then element count is 3. And we did say that these buffers were giving vertices and colors, correct? And buffer type static vec3, definitely. This looks good. Okay, so I'm going to assume that the buffers are loaded correctly, but we're not setting them correctly. So let's bind the entire VAO and then the buffer. And then we can enable them. So let's do this. And let's also make sure that this is correct. Enable attributes, get attribute name, location. And if I, that's what we did. We bound the buffer, we got this, and then we buffered the data into it. And then we did attribute location. We might need to bind both the VAO and the specific buffer, and then do that, which might make sense, because once we bind the VAO, it might not associate this. Yeah, it's not associating potentially the VAO with this attributes binding. Like connecting this data to this attribute should also be part of the VAO, which makes sense, because we only bind the VAO when we draw. We don't bind the buffer, and so when we bind the VAO has no idea that there are attributes set at all. Okay, yeah. So potentially we actually need to bind the VAO itself like this, and then set it so it associates this data with the VAO, with the VAO, that we can enable them. So let's try. So this is vertex position, and we need the vertex color, and this time it's buffer1, buffer1, buffer1. Let's see. No, still no. Okay. Finding. We'd soon also need to be thinking about debugging. Like this kind of thing. It's doing, okay, what state is inside OpenGL? What's happening there? But I think for now it's simple enough. All right. So you have the attribute location, vertex position, and yeah, position, color, activate, deactivate. We might need to enable them as well before we disable. Let's see. Oops. Like crashing. Ooh. It's crashing now. Interesting. That's interesting. So let's maybe enable them just before we draw. Let's set the background to white just to make sure we don't have black on black kind of. Clear color is all black. No, please give me white. Yeah, we don't have anything at all. It's so shocking. Okay. So So the only difference from what was working before is in here we did everything in one go without unbinding the VAO and then binding it again. So do we really have to kind of do this in one go? Not sure. We can test, we can uncomment this and then try. Definitely. Which we know works. So var VAOID. We can try doing it in two steps where we just in the middle we unbind the vertex array and then bind it again, which is what we are essentially doing. What's wrong? Shaders. Import cycle not on. Oh yeah. Don't worry about it. Can this in a minute. Yeah, let's try. Let's try. So we bind this. Let's also bind, which makes sense, bind the buffer. I think we forgot to do that now. So this buffer, just before we, like, we're saying it, hey, you know, this data, send the data to this thing. It's like, what data? Well, we need to activate the buffer. And then next time we need to activate, so we activate the VAO, and then bind the buffer essentially, and then bind the second buffer for using. So when this happens, it knows, oh, okay, it's this buffer. That's running. Why are you sad? This is new shaders. Okay. Nope, it's still not happening. So we are binding the two buffers. We're binding the VAO, two buffers, doing this. Let's do everything with just vertices for now. Just for now. Just to see one simple situation. Because it could be that, okay, it's recording, since we are disabling and then enabling again and binding, it's only recording the first one and not the second. So now we have this thing, and let's make sure we're enabling them after. Oh, we're not enabling them. We should enable. All right. So let's also say actually simple shader dot enable. I don't think we're enabling anything. Yeah, we're not. Vertex position. Let's see. Maybe. Oh, crashed. So if we enable within the VAO, it crashes. Interestingly. What we had before, let's see, what did we do before? So we made the VAO, but then as the VAO and the buffer were both bound, we filled the buffer, so the VAO is recording that, and we set the data all in one go. Yeah, and then we enabled it immediately after. So with the VAO bound, we set the data, so and enabled it. So why is it crashing for us? It's very interesting. It should. This should work. We can debug now to see kind of. So we're replicating that more or less. We have this, which is here, right? So for us, step one is we do this, we bind the buffer and fill them. So we fill the buffer. Then let's try. Should we not unbind before? Yeah, interesting. So now it's not crashing, is it? Oh, I didn't save here. Okay. Activate VAO, find the buffer and the VAO. And then do this and enable. Oh, crashing again. Oh man. Okay. This step through the code. Stop it here. Oops. Run and debug, please. Where's the running? Oh yeah. Just yes. Okay, he's done. Take ages to build. Right, whilst building, we can review the code. So by this point, we have already loaded the buffers. That means we should have data in the buffers. Right. Now we want to kind of load again, and then we should bring back the buffers that we had, bind them as well here. And then we're filling up the attributes. Either this or we do everything in kind of one step. So as we set the attributes and everything, we don't unbind the VAO, but I think that doesn't make sense. That this is a requirement. I don't think so. So let's see. Why are you taking this? Oh, come on. Okay, do it. Okay. While this works, we can check. Is disabled. Bind, buffer it, and set the data. And then use the program, right? GL use. Yep, GLRA buffer still bound. So binding the data is just to the buffer, GLRA buffer. It seems. It's not really related to anything else. It's related to the buffer, right? So it's as long as it's bound, calling this thing before we unbind it is good. So yeah, enable vertex attribute. So we get the location by the time we enable it. Should we enable it right after? Maybe. You are not running it well. What are you doing? Okay. Here's what we're doing. We're filling up, and then we're binding, and okay, this is not working today. Yes, please. Just launch. Finally. Okay. So we have OS starting screen. Let's check buffers. How does buffers? We have one buffer as expected. ID 1. Okay. Array buffer. There we go. And some data, which is correct. Right. It's a vec3 Each element is 4. We have 3 elements, and this is the type, which is GL float. Good. We get this attribute locations like 0, 1, 0. We fill it up, we enable it, we deactivate. We run. Let's go to draw. Clear. Activate the shader. Activate the VAO. Draw the array. Ooh, there we go. There we go. So drawing fails. Got it. Interesting. So let's make sure we're drawing the right way. Use bind the VAO and it's right. Vertex attributes. Okay. Is how many entries? 3 vertices. Yes. Okay. So we do have 6, I think. Buffer the vertices. So we activate, we bind it, WordPress. This looks fine. Now I assume if we do all of this in one go, right? Like it's essentially returning to what we were doing before. So we take this and immediately we generate the buffer. We generate, let's put it here, bind the VAO, bind the buffer, and then let's see, and bind VAO for buffer. Open here. What does the internet say? Okay, so vertex array, resume for you guys. This is the same. So bind it, bind some buffers, fill some attributes, enable the attributes, then I bind that. Do we have to? We don't. I mean, we did this before. Point is not having to. Yeah, we only bind the VAO after that. Here, yep. This array, VAO ID. Okay, let's go to this thing. Just make sure that we have valid everything, valid ID. Yeah, this looks valid actually. VAO 1, buffer 1. And make same. Yeah, we're done. here. So we bind the VAO, we create that, we fill it up. Let's review this logic actually. So you have the type, buffer type is where is this buffer type? GLI. Let's make sure we're using that correctly. Yep. Array buffer, right? VBO, we create a buffer. We have a buffer type and in the ID. Then we buffer the data in that. Let's see. Element size into the data. This thing into the size in bytes. And in this case, we are getting this. Okay, let's just look at the debugger. This one. I have to run from main with the debugger. So you have the buffer. This thing is 5. We look at data types. The 5 is pick 3. Yeah. And that is returning to us element size 4 bytes, country, and we have n, right, element size 4, len of data is the vertex positions, yeah. 18, 6 vertices, okay. Then the pointer to the data. Is there any buffer usage? This looks fine. We buffer it. We can check. We create vertex array. Bind. We bind the buffer. It's an array buffer, and then we 4 into this. That's it. We're done buffer. Append this buffer to buffers. So now buffers has one element, which is this thing. Okay. Activate application 0. Yeah, speaking of which, let's remove color stuff for now just to make sure our stuff works. And let's hard code the color for now to white, so we can actually see. This one. I would like to really get this to work today, so we have a nice stopping point. Okay, so it's still crashing when it's drawing. Vertex attribute. Okay, size. 3 elements of this type, not normalized. Stride distance between one and the next is the total size. In this case, 0.3, which is correct. Okay, and point offset 0. Oh. Let's see. Does pointer need anything special? Slice pointer. Buffer is bind buffer, and okay, there it is. Buffer objects binds the. Let's put this down. Buffers, and then you have this here, and the buffer. Okay, so you have buffers, and then just to arrange things. Okay, so buffers does bind buffer and then unbind using its type, which is just for now array buffer. Okay, and then we gen by sending, by creating a new VBO, storing it using its data. As far as this goes, I think this is good. I don't have any idea why this is wrong. We can try now moving the code here just to see. So we generate and then we'll immediately do this. Okay. So normally, like last time, we did this, which is we know attribute location is 1, I think. You can see. Here. Attribute location. Yeah. Just do 0 for now. So we have this, and we have I just see if doing it in one step, because last time we did in one step, everything works, and I'm not sure what is going on. Just enable attributes, vertex array. It needs a view. Wait a sec. Vertex attribute array. Vertex array. Oh my god, I think we weren't enabling attribute array. Vertex attribute array. Wait, oh, that's okay, good. There's vertex attribute array and there is a vertex array attribute. Okay, that's sad, but okay. Vertex attribute array, generic vertex attribute index, yeah, because we know that this works. And vertex attribute pointer and vertex attribute. So we want to enable this array since we are bound to the specific buffer. We bound it, and this should exactly replicate what we had before, and hopefully draw something, and then we can start changing within before moving to functions. Oh, this is dying again. Interesting. Even though we are doing everything in one place. Sorry, let's come this out. So here we are not doing anything. Load buffers, we're doing only one thing. Load buffers, we have vertices, we call this one function. We're in one go right now, at least. We bind VAO, create the buffers, fill them up, and then point the, set up the attribute and enable it. Before all of this, before I'm binding anything. This should be exactly what we had before, but it's not. This is very confusing. Okay, let's do this. Shouldn't matter honestly, but let's do get size. Kind of replicate exactly what you had before, and then we can work backwards. Oh, it could also be this is a 1, not a. Okay, yeah, it's 1. So you have this again. Vertex position, but it's not being passed correctly. See if it's not crashing anymore. Maybe the data. Maybe the data, honestly. Buffer and then buffer the data. Okay, bind the buffer. And the size of the buffer is this to this. And GL static draw. Attribute location. I think we can force it just to make sure we can test layout equals 1. Layouts. I forgot this syntax. Oh, okay. Layout location equals layout vertex header. Yep. Okay. It's layouts. So here we're kind of forcing it to be at a specific location, just for testing at least, so we know it's at 1. Okay, so it's at 1. Now we're crashing again. Let's also see if we can get open. Yeah. Access violation. Pointer is dereferenced to inaccessible memory. So it seems it is the data. This is nice. Let's see. It's the same model. This is index. Okay. Yeah. We know some kind of data issue. Let's see if we copy all the vertices, put them right here. And run. Nope. Still same issue. So we have data. Here's some calculation problem somewhere. Element count is 3. That we should know. Why? gl.float. Oh my god. Oh, the type was wrong all this time. Okay. None of this, none of this. Oh wow. So we made a mistake in the data type. GL type should be the type of the element. not the type of like, is it a, we don't care if it's that, like we might as well have it, but like it's not the GL type. I don't know where you would use this, but like, oh my god, no. So here we'd want an element. We can keep GL types, we already have it, but oh my god, it's so we were passing. So we should have said when we're filling the attribute that hey, we have some type. So we're saying like, oh, I have three GL floats per vert position. They have 3 GL floats, right? And here is like the size in bytes and whatnot. And instead, we're saying float vec. And so the array was completely off. The buffering, sending this buffer into this variable was completely wrong. Oh, all right. So instead, so we can. I hope the rest is fine. Doing it in multiple steps and everything. So the data, we'll keep this element size. Everything should be okay. Binding, all of that. Adding the buffer. The buffer is ready at this step. I might as well add it here. But yeah, so this should be fine. This should be okay. All of these, I mean, we'll test right now. But what we need is data type. We need an element type. So in here, each element is what? Right. So in here, the element type is just the element. It's the same. In here, it's going to be the same. Element type. In here is going to be each one is a double. Each element is double. So here's now in here, while the whole type is vec2, and you might as well just keep it. The element type is a float, and this is what we care about. When we say we have 3, it's 3 floats. 3 floats, not 3 vec2s, or like 2 or 3 or whatever. So here is all. But oh my god, this was well, it's very easy to miss. Okay. This is the type of each primitive, e.g. for vec3, it's GL. Of the it's the type, the variable. It's float underscore vector. I'd be interested in saying, hey, if we say one float vec3, if that works, we can test, but we'll do it one step at a time. So you get these, and now this should be correct. Element size into data. This is correct. We in the shader program. Like you're wrong. Fine. Okay, now you're happy. The only difference is it's not the GL type when we do this. It's the element. And then we say, hey, of this type, of floats, we have 3 because it's a vector 3. And then in main, we just load the buffers. We set the attributes, and we should enable it. Where's enable? There we go. And enables this. Yeah, that takes long. And drawing is simply this and this. That's right. Oh no, not again. At least I'm crashing. So in here now, this is probably where we come to bind and so on. Set attributes. Now we need to bind the buffer, right? Let's see. So you have the data, so it's okay. And to set it, we do this. Okay, so let's return to our original test now that that bug is fixed. Using our test. Do we need to bind the VAO? I don't think so. It's just to the buffer. But that's what we are here to test. So if I activate the buffer and then at some point deactivate the buffer, right in the middle, we're going to set it. So we do VAO bind in the buffer, and then we again at a later point in time we do this. GL type is wrong. We said this is element type, and the size, the stride essentially. This should still give a back screen. Yeah. Now, what if we do the VAO as well? Interesting. So we do need to bind the VAO when setting the attribute point as well. Now let's test our other hypothesis. If we do, so if we say we have always one, not element type, but one GL type. So instead of saying I have 3 floats for a vector 3, what if we say I have one vec3? Does it work? No, it does not. So I'm not sure what that is used for. So we'll stick to this. Yeah, this is nice. This is nice. Oh, we're already 2 hours and a half. I guess we can stop soon. We now know this. We just need to edit our set attributes. Is it not taking a buffer? It needs to also know about the VA. Right? The buffer needs to somehow reference its VA. So instead, we can send maybe a buffer object, and we can send an index. Yeah. Well, I have a question actually. What if we only bind the VAO? Does it work? That doesn't make sense because it won't know which buffer it's using. It won't know. Yeah. No. If we do this, then it works. So we need both. So later on when we bind the VAO, it knows kind of okay what to do. And one thing also, can we enable after the VAO? Does that work? Yes, we can. That's separate. That's independent. That's good. So we need to bind both. So we need to say send me the buffer object, and you need to tell us which view you're using. Buffer objects. No, we can follow a similar structure instead of arrays, just like we had vertex shader, fragment shader, so on. We know, like, okay, our as far as uniforms are a different thing. We can look at those later, but as far as these goes, like, okay, here are the inputs per vertex information. So there might be like specific, we have colors, you know, UVs, these things. I'm not sure if you have yeah, that'd be different. I'm not sure if, yeah, we can hard code. Let's see, like this, we just have some amount of inputs per vertex, which we can increase once we're loading more advanced stuff per vertex. Or we can go generically. For now, I think let's go and say you have to send me the object, so I get the VBO, and please send me the buffer itself, or the index, buffer index maybe. Maybe that's more annoying. Yeah, this is annoying to use. So instead, we can give it an array, but we give each one a type. Sure. Or we index kind of the VAO in the buffer as well. Let's see. So buffer objects, example, can give each one a type. Like aside from this thing, we can say, hey, is this position? Is this something else? Buffer usage. We're using this. Yes, we are. So what do we call this? We can say, yeah, I mean, we can send a buffer, honestly. I guess buffer is a buffer. We can send VAO ID. That works. That's simpler. Yeah, uint 32. Now we can, or send both, just so we can use the nice functions we made. So we can send a buffer and also the buffer objects. You can maybe improve this later on. Object, and so we have to activate the buffer and the object. So the VAOs, the VAO recognizes what's happening, and then at the end you can unbind the VAO and then unbind the buffer. This thing, element count, element type. That should be it. That should be good to go. So again, let's try one more time to all of this and use our nice little functions we have. Set attributes will now take the buffer and the buffer objects for the Vertex position. All right, let's do this. Oh, here we go. Here we go. So this is now nicely done. So now we can remove all of this. It should still work. Now we can do multiple buffers like colors. Color. So we do this, and then we simply set and enable the vertex position. Let's set and enable on buffer 1 the vertical. But yeah, like the problem is also, again, we're indexing here and we don't know the order, so I think we'll just move it to B fields. All right, perfect. Now these are not being used, so we re-enable these ones, and the fragment color we can take from the input. Try again. Oh, what's happening now? Birds. Ooh, bird color, not bird position. Yeah. So yeah, this is the vertex position. Oh, we need to enable this as well. Yeah. So to pass on the color to the next one, and then this will have an actual value coming in. Okay. Now we should see. Yes, we are back. Very nice. Very, very nice. So you can have maybe some nice red at the bottom right. This one. So we have kind of 2 red, 2 blue. Or red at the bottom, at the top. So top left and top right. Second vertex. And we'll do all of this later on. All of this will be coming from a file. So maybe we use Blender, we call it all on there, we get some file. Yeah, that's pretty nice actually. Because we have a seam in the middle, that's why. So we read all of these and we can associate all of them together. We have like resource loaders and so on for the different types of objects we have. So let's return it to being. Cool. Now, so one last thing for today is let's take these buffer arrays, since they're really not nice, and we just have multiple buffers. So we have vert post, and this might not be the best way to do it, but I think vert position, color buffer, etc. So as we need, we just kind of have end potential buffers. And the buffer type, yeah, if the ID is 0, you know, it's not set. You can potentially make them pointers just to reduce the size, so we don't have a ton of data floating around that we don't use. We don't load all of them. So then this is not needed. Instead, set buffer, and in the buffer we can say buffer name, maybe buffer class, buffer GL type. So we have data type. So we just now need a way to kind of know, okay, is this a vertex Word position buffer, color buffer. Yeah, word position. So is this color buffer? Is this what kind of buffer is this? Not in the data type, but probably in the buffer itself here. So eventually we can have, I just don't know what to call it, type or class. And it's just like, okay, is this buff class to which class I know, right? Then word position color. Maybe you can call buffer attributes. Buffer class or, and so here we can have just a small function on the object itself. You can say buffer. It takes just a buff, takes a buffer, and just we have a switch statement on the buffer class. Buffer type. Buffer. We can also do buffer GL type and just buffer type. Buffer info type, data type. Yeah, maybe info type. Sure. Buffer semantics. Info, data type. Yeah, info type is the same. So buffer is I'm not sure. It's kind of confusing. We want to say what attributes it belongs to. Yeah, I guess the thing that makes most sense is just this buffer type. So we can name this. So this is buffer GL type. This is the buffer type, and we might come up with a better name later, but this is good, I think. Unknown, this, and we'll do a similar thing as we did before. So we can now look up. We have to add in the buffer. So each buffer now has a GL type, and it has type. And we can explain these in some comments. So when we gen buffer here, we can also specify, or we can ask for a data type buff usage, buff data type, and we have buff essentially. This becomes buff GL type. Type. I'd like to remove this, but let's. So we can maybe have just different generic buffer and gen something else buffer. And then this kind of the GL type is hidden below. Actually, let's do that. I think gen. Yeah. yeah, we can just do gen buffer. It's the kind of the normal buffer. And then if we have special types like the depth buffer maybe or something, then we can say, okay, we can have another function. Okay, this. So now we don't have the real type that we know. So you just give us your usage and the type of the data type. And here we can say your type and oh, we still have class. Okay. Buff GL type. Okay. Now, instead of an append to an array, we can have a function like set buffer, and it will just look the buffer type, and if it's like buff type word position, we do word position buffer is, and then if it's buff type word pos, yeah, color buffer is this. If you want, you can, like, if you really need you in full control, you can potentially just have, along with these set ones, you can have two other functions where there is an array of some random buffers, and there are some more generic functions that are harder to use. But for now, I'm going for ease of use as much as possible, something that's understandable, potentially library that people can use later on. So we can say logging dot for log.line unknown buff type in type is, I'd like to use some better library for logging. This isn't very good. Zap is really good for these things, but okay. Type is, and we don't do anything. That's it. So here in this case, so we create the buffer with everything. Type is buff type that we got. This is set. VBO is set. Here we just call, hey, VO set buffer, and there you go. You can make a pointer and you can do this. And then we do all of this magic. And this is it. And in main, now this is no longer here. Usage, data type, and buffer type. Right? Buffers dot is the vertex buff type word pause. Same here. This, and we say buffers dot buff type color. Now it's much nicer. Say here are some vertices, and yeah, here is like birds, is it color, so on, like what are we doing, and then it sets that based on that. There we go, and everything else should be unaffected. Oh yeah, so we can simplify now this, I think. So instead of saying, okay, you know, God knows what index this is, I can just say this is my vertex buffer, and we can make it take a pointer. So here's my buffer object, and Then we can use this thing. We can maybe simplify even further later on, but at least we're not doing some random indices that we don't know. This is complaining. Mixed named and NA parameters. Oh. Okay. So we said testing, and then again, this gets nicer. This is the carbo. So with this, so we set attribute this thing with this buffer object and this buffer and so on. And we should be able to see the same thing as before. Yep, but with a nicer interface. Okay, and I think this is a pretty good stopping point for today. Thank you all for coming. It's been a bit longer than usual, but I think we got to a pretty good place. Now we can even remove all of this. We have a much nicer interface to use things. If we load our data, maybe we'll do this next. Maybe we'll work on a small game like Space Invaders. I would like to start using this as soon as possible. We still have a few things. Maybe loading images, and having something higher level than buffer. So buffers are good. It's like 2 calls, like buffer attribute. So we'd maybe do uniforms, and then we have things like 3D model and sprite and so on. Some higher level things that underneath use buffers, but we don't have to care about the specific things they're doing. So I guess we're starting with a bit more of a graphics library in the beginning, not really a full game engine, but then we grow from a graphics library into game engine with entities and having like event systems. That'd be very interesting. So yeah, thank you all for coming. I hope you enjoyed. It's getting pushed as usual to GitHub if you want to follow. And today, so we're going to push this. This is episode 4. Buffers package. All right, everyone. Thank you so much for coming, and see you next week.